he has been always, doing a lot of work for the students. I am so happy to see Dr. Mona Lisa Mohapatra,
Right.
who is going to be the academic counselor for
Right.
our learners. And so, friends, I really wanted to. Can we just? Can you please, Radhasmita? Can you mute yourself?
Students kindly put your mic in the mute mode. Whatever one you want to ask, and you can
Yeah.
unmute and ask.
Exactly. So I was saying that, see, I just wanted to have a face-to-face, this one with the learners, because this is for the first time, I think we are holding online classes. I mean, formally from RC Bhubaneswar, and that too, I mean, across the country, whichever study centers or the regional centers, they will, or the students will be connected to this particular one. And I also ensured that, since, January 22 students are also still eligible to continue the program. So I have invited, all those students who are January 22 to January 23. So there were a number of emails which were available with me from our SRD division, and so I invited all of them. And really, I say, all for all those students who have today logged in, I think it's actually a very good opportunity for all of them to interact directly with the teacher. And a few things, of course, I am sure, the regional center and the, I mean, people associated with this, they do apprise our learners, about the way these academic counseling sessions go. But still, students, since, maybe, this is only first and the last time for this particular schedule which has been given to you, I would be interacting. So I would like to tell you that you know that you will have 6+1 counseling sessions here. A piece of advice to all of you, which Dr. Mona Lisa will also tell you, that come prepared with your study material. The study material is available to you. So please come with your troubleshoots. Like, wherever you have a difficulty, you can come, you can discuss with Mona Lisa ma'am, and she will not only deal with your academic problems, but also anything related to administrative, since they belong to the regional center. So I'm sure, lots of queries which I get through emails from the students will be sorted out today. And, they are going to have a real opportunity. And for that reason only, because this is our since, you are coming in contact with regional center straight away, a piece of another advice is that please be in touch with your study centers. Your studies here, have come for theory counseling, and different teachers, the assistant regional directors or other experts will be dealing with different courses of PG diploma. But your lab counseling will take place in your respective study centers. Please, learners, take care that you remain in touch with your coordinator, because we teachers, the faculty sitting at the headquarter, may not, know the schedules if it is not posted on the website. Do keep checking your website for the latest schedules, and always, write an email, contact through the landline numbers which are available on the website. And, before taking up your exams, please see that all the assignments are always uploaded on the at the website. So whenever you have a problem, go to the website and download your assignments. Don't wait for the hard copies. Again, taking advantage of this opportunity of interacting with you, I wish to tell you that there, we have a Vyas portal at our IGNU website. So this portal is web enabled academic support for the students. It has been activated for our PGDAC learners also. I would be sending you the mails. Please connect to this portal. We will have a discussion forum, so we can, discuss with, you can discuss with your peers, with your academic counselors, and so on and so forth. It's going to be a good learning for you. I don't want to take very long time. I wanted to just check if any of my other faculty members who are associated with different courses. See, we like I am coordinating this particular program, and also one of the courses that is spectroscopic methods. So similarly, we have Professor Malhotra who is coordinating our separation methods course. Professor Fosdat, he is taking up electroanalytical methods, and Professor Komalika Banerjee is for the basic analytical course, which I think Dr. Mona Lisa will be taking up. Isn't that? Yeah. So
No, ma'am. I'm just going to teach the spectroscopic methods only.
okay, okay, that's really great. I think,
Ma'am, just I'm sorry to say one thing.
yeah,
Whatever the schedule is given to you,
yeah,
instead of MCH-1, now ma'am is going to teach MCH-3
perfectly
because
fine.
it is
Yeah.
because my same teacher, but just little changes.
Okay, okay, okay. I think there is no problem, sir. Anyways, you can go the way you schedule, and it's left for the learners to take advantage of this opportunity, I would say. And anytime, please, our dear learners, if you feel that you want to contact us, do come up with the email and do access the IGNU website. Always keep yourself updated. I think Chandan Goswami has raised the hand. I don't know if he or she wants to say something. You are welcome, please. Do you want to say anything, Chandan
Uh,
Goswami? Yeah.
hello,
Yeah.
hello. Good evening, madam. I am from Kolkata. Myself,
Okay,
Chandan Goswami.
okay, that's great.
Actually, madam, we are very pleased that you attend this our session and organize in very good way, madam. Thank you, ma'am, for this for allowing us to attend
Yes,
such type of program,
yes.
ma'am, online through. Madam, actually, I have admission in 2022 June. Already 1 year complete and
Okay.
a written exam already done. Now it's
All
time
right.
to give only the pending lab course. So
Lab
the
courses.
if you kindly organize same thing, so we are very pleased, madam.
So,
And ma'am,
so sir,
also
I would
one
like,
more thing, ma'am,
yeah.
assignment are not showing in the website. We don't know the
No, no, no.
exact time the evaluation of the assignment.
You
Yes,
mean
ma'am.
the assignment booklet is not available?
No,
That
no,
is what you
madam.
mean?
Those
Yeah.
students, those who have already submitted their
Some,
assignments to the
yeah.
study center, but the
Yeah.
result, the evaluation of the assignment is not highlighted in the website or in the UGNI site.
Okay, okay,
So
okay, okay.
we don't know the मतलब क्या हो रहा है आगे का फर्दर
हाँ,
नेक्स्ट स्टेप्स वी डोंट नो अंडरस्टैंड
बिल्कुल सही। ऐसा है चंदन, आप को मैं एक और पीस ऑफ एडवाइस टू ऑल द लर्नर्स, जब कभी आपको
yes
यू हैव अ प्रॉब्लम ऑफ दिस काइंड, please get back to your study center. You know that it is
yes
your study center to whom you submit your assignments. If they
yes ma'am
suppose it's not uploaded, ask them to send a copy. You can send it to me also. I will see if it can be uploaded from the headquarters. So for anything,
okay
learn that you have to be in communication. All right.
okay okay ma'am
We would
thank
definitely,
you ma'am
all right. See, I am
thank you
saying,
ma'am
all right, all are most welcome. I am saying another thing is that the lab courses, as I said, will be conducted at your region, at your respective study centers. So please take care that you be in touch with your study center coordinator. Always, I mean, catch hold of your coordinators. Tell them to do. Suppose there are not many students. One piece of advice again, tell your coordinators to combine your um, lab counseling with
lab
the,
course
yeah,
yeah.
lab courses with the ones where UG labs are going on. Suppose only two or three of you are there in a study center. Please ask
Yes
your study center coordinator that they may combine your lab courses with the ones going on for the bachelor's BSc program. All right. So
yes
that's
yes
another way you can get your work expedited, because you have only 3 years with you. Don't forget that.
yes
And good that you
yes
have
ma'am
cleared your theory
yes
exam.
ma'am
All the best.
thank you ma'am for telling some type of solution ma'am thank you ma'am
Sure, sure, sure. Uh,
thank you ma'am
okay. okay. If anyone wants to, or sir, Dr. Panigrehi, anything
Yes,
else?
ma'am.
Anything else? Because I would not come in between Dr. Mona Lisa and the learners, because they would be eager to interact with her, know a lot more. I'm sure. Sir, anything you?
Thank you very much, ma'am, for your tips to our learners. And learners, if any problem regarding assignment or the lab
Yeah,
course, you can write to your study center or write to your concerned regional center. Definitely, will reply to you and we will conduct according to that. Don't worry for this.
yeah.
And thank you very much for your time, ma'am. So now, the students, this is small changes and small announcement. Today, you are not going to start the MCH-1 because ma'am is going out to Kashmir. Because of that, then you have to change a little bit. Instead of MCH-1, ma'am will take the schedule is same. Teacher is same. Only with that change, because instead of MCH-1, you are going to start today MCH-3. Okay?
Right.
So, I welcome you, Mona Lisa, ma'am. So now I hand over the session to Mona Lisa, ma'am. Ma'am can continue up to 7:45.
Okay. Sir, I'll take your leave. Wish you all, I mean, the very best, all the learners, I mean, the regional center. And of course, thanks. I want to really thank Dr. Tripathi for taking this initiative. Thank you very much.
Thank you, ma'am. Thank you for your kind words.
So should I start or should I
Yes,
share my
ma'am. You,
slide?
yes, ma'am. You start.
Okay, thank you. Please, all the students, please mute yourself. Is my slide is visible?
Yes, ma'am.
Yes, ma'am.
Okay, fine, fine. Thank you. So let me introduce first myself. You should know your teacher from the beginning. Myself, Monalisha Mahapatra. I did my PhD from IIT Madras, then postdoc also from IIT Madras. Then now currently I'm working as an associate professor in Gangadhar Med University, Sambalpur, that is in Odisha. So today we'll be discussing your spectroscopic methods, that is MCH-003. Since this is the last class, let me first give a glimpse of the idea about the PGDAC theory part. So you will be covering in this theory, this program, that is basic analytical chemistry, which is MCH-001, then separation methods, spectroscopic methods, which I will be starting today, then electroanalytical methods and other some methods which will be a good way to understand the analytical chemistry. So that basic analytical chemistry, there you will be covering the titration methods, neutralization, acid-base titration. So these are small basic concepts and you need to go deep of that subjects. But you have already studied during your +3 and +2. You have some idea, that is neutralization, what is neutralization, what is titration. You are having some idea. Then separation method, you will be covering your chromatographic techniques of separating two liquids or liquid solid, like that. So that is also some way is known to you. But spectroscopic method is complete. We are starting from your, you can see here, that is molecular spectroscopic methods. We'll be covering UV visible, IR, Raman. So various spectroscopic methods. It is a very, very vast and difficult subject out of these four things. So you have to listen me very carefully. And since we are having less time, 6+1 class, so we'll be covering it soon. But whenever you are having doubt, you can ask me. And for your simplicity, I'm going to take the classes from the study material which is available to you. I'm not preparing my own slides or own something which will be very difficult to communicate with you, and it will be difficult to understand for you. So you can go through the study materials which are available to you. From there itself, you can learn something. Then again in the next class also, if we are having doubt, we can discuss, but we are having shortage of time. With 7 classes we have to complete these 5 blocks. You can see here that infrared, Raman, then fluorimetry, application of the fluorimetry, flame photometry, AFS, AES, everything we have to cover. So this technique you need to understand very well. May I know, you people have already studied PG chemistry? I should know who are the audience first. Accordingly,
Yes,
I
ma'am.
can tune my teaching.
Yes, ma'am.
Yes, ma'am.
PG chemistry you have completed.
No, ma'am. No.
Yes, ma'am.
Yes,
No,
ma'am.
ma'am.
Okay.
Yes, ma'am.
Okay. Few have completed, few not. Okay,
Yes,
fine.
ma'am.
So those have completed, for them it will be little easier, not exactly easier, but spectroscopic, they know that spectroscopic is a part of chemistry technique where you need to understand the spectroscopic thing very clearly, which is completely unknown to us during our plus 2 as well as during our graduation also. In PG only we start reading these parts. So those have not completed PG, they also listen to me very carefully, try to connect. If they are having some doubts, they can ask me. But it's really tedious to complete within all the things. So let's start with the light. Okay. So this thing we are able to see, and nature is very beautiful. All this is because of spectroscopy. How? That this thing comes from the matter and light interaction. There is light and matter interaction. So if you say what is spectroscopy, then you must say this is just the light matter interaction. That is the origin, that is the mother of spectroscopy, light matter interaction. So this thing comes from the light matter interaction where your dispersion, scattering phenomena, everything is consisting of. Okay, but light, when we these things we studied during our plus twos, if you remember, then what is light? That is having particle nature or wave nature. Always, when we think of some science, there is always we rethink it in form of research going on, research. We keep on doing these things, right? So, whether it is having particle nature or wave nature, then Newton come with some ideas that light is having particle nature. It is having reflection, refraction, which is showing the particle nature of the light. Then Planck agreed to it through by doing experiment, that is black body radiation experiment. He agreed that yes, it is having particle nature. Then Einstein also agreed to the point, yes, it is having particle nature through the photoelectric effect. This black body radiation, photoelectric effect, reflection, refraction, this all you know during your plus twos. In physics also, in chemistry also, the basic things. That we'll be discussing also later on. Then, then some scientists came with idea that it is having wave nature. That is, Huygens, light is having wave nature, he told. Then Young agreed to it by doing double slit experiment, which you have studied in physics. Then Maxwell also agreed to it by through electrodynamic theory. But then these people told it is having wave nature, the other people told it is having particle nature. But how they are claiming it? Always through experiment. Always through experiment only we can claim something. Then later on, the de Broglie and Heisenberg you might be knowing very well de Broglie's law and your Heisenberg uncertainty principle. They nullified the both the groups concept, that is having particle or wave, but they are saying it is having dual nature. Okay, so it is having dual nature, both particle as well as wave nature. We are not going too much deep into that because you will be reading in the physics classes, that is a component of physics classes. But coming to the spectroscopic part will be extracting from that light matter interaction is your spectroscopy. You need to understand this 5-10 minute lecture, then only you can coordinate with other blocks, other units. If you are missing here, then it will be very difficult for you to understand spectroscopy. Okay, so listen to me very carefully. So study of light matter interaction. Light is having your electric field vector as well as your magnetic field vector, and both are perpendicular to each other. This you know very well, and this is a particular characteristics of a light wave, right? This is a particular characteristic of a light wave. So now the thing is, this category you might not have studied in any book. That is molecular spectroscopy. This is the effect of electric field interaction with that of matter. And the resonance spectroscopy comes due to effect of magnetic field vector of the light wave interaction with the electron and nuclei. So spectroscopy, if you think, then you just imagine yourself that light is interacting with matter. Out of that mother interaction, you will have your rotational, vibrational spectroscopy, electronic spectroscopy, under which your Raman, IR, UV, which you might have heard about. Then from resonance spectroscopy, this NMR and EPR are the resonance spectroscopy. Then here you see very carefully. So when you are saying that light and matter is interacting, but simply we can't say, okay, this light ray is coming, this is interacting with the matter and something is happening. But that something is what? Due to that interaction, due to the wavelength or frequency of radiation and that interacting process, what is happening, based on that, your light wave has been divided into your various spectroscopic regions through electromagnetic spectra. Through electromagnetic spectra. Now the basic thing is, if I am giving a punch to you, then what you will do? You will be moving like this, okay? If or some changes will be happening at that place. So just because you are putting some energy to it, you are putting some energy to it. So now you see very carefully that depending on the wavelength and frequency, you are dividing the electromagnetic radiation into different sections, that is cosmic ray, gamma ray, X-ray, ultraviolet, then visible, which is the smallest space it is taking, then infrared, then microwave and radio. Now you got an idea, depending on the wavelength and depending on the frequency, there is interaction. So now if radio wave frequency region radiation is falling on matter, what is happening? What is happening in that region? There we are categorizing the spectroscopy to be NMR spectroscopy, EPR spectroscopy. It is coming in that region, NMR spectroscopy, radio frequency region. Then microwave region radiation, when it is falling on the matter, that time we can study the rotation related phenomenon of a molecule. See, the thing is, When radio wave frequency region is falling on matter, that time you are not going to study rotation part or vibration part or electronic transition part. For specific wavelength and frequency radiation, you are going to deal with the specific spectroscopy. Okay, so microwave region radiation, when it is falling on the matter, that time the rotational parameters, rotational phenomenon involved in the thing you can study. Okay, so that is why you say to me microwave spectroscopy or rotational spectroscopy. That comes in that region. Then when IR frequency radiation falling on matter, that time vibration, related vibrational things comes into picture. So that part of spectroscopy, we say vibrational spectroscopy or IR spectroscopy. Then when ultraviolet or visible region radiation falls on matter, that time the electronic cloud, that delocalization and electronic excitation takes place. And here we say absorption spectroscopy, emission spectroscopy, under emission, again fluorescence spectroscopy, phosphorescence, delayed fluorescence, all that will come under this UV visible region. Then coming to the X-ray part, when X-ray region radiation falls on matter, then bond breaking, ionization, these things happens. Here your EPR spectroscopy comes into picture. EPR, mass, all that will come. Then, when gamma ray falls in your matter, that time Morse bar spectroscopy. You might have heard about Morse bar spectroscopy nowadays. Actually, from the textbook also it is missing. Slowly, it is getting edited, that Morse bar spectroscopy, because gamma ray is very, very powerful, very penetrating, and very energious radiation. Nowadays, in laboratory also, we are not dealing with the gamma ray mostly. But you will be finding it in your Kalpakam or BRC, wherever you're having some energy related matters are going on. So here you can see, if you see a electronic process, here in this diagram you just see my electronic ground state and excited state where it is mentioned. I just want to have a feel of this thing, that a molecule, when it is in the electronic ground state, it is absorbing certain radiation. Then after absorbing, it is absorbing some energy, so it is going to the up excited electronic state. Then when it is going up, it has to come to the ground state. How it will come? It will come by releasing some energy in terms of light or in terms of heat dissipation, in whatever way. So in that way, if we'll see, then you can study the absorption and emission spectroscopy very well. Now, these slides only I prepared to have you a feeling of the spectroscopy and different regions of spectroscopy. Then now onwards, we'll be focusing on your study material, which is available to you. You can download it today also. You can read it carefully. If you are having doubt also, we can interact daily for the 7 days. Okay. So now I am moving to the study material. We will start from the part which you are having in the course. Okay. So any doubt you are having here?
Oh, ma'am.
Any doubt? Okay.
No, ma'am.
Maybe all of you are clear with these doubts. Let me, Dipti Ranjan, can you mute yourself? Better.
Ma'am,
Hmm.
ma'am, I'm Priyanka Joshi, and
Yes.
actually, I want to ask you one question. That ma'am, what is the difference between spectroscopy and spectrometry?
Metry. Okay. Spectroscopy is a method of studying. Spectrometry, when I say it is a fluorescent spectrometry, the instrument through the technique I am using to study that method. That is what is spectrometry. I say spectrophotometer, or I say fluorimetry. Fluorimetry means the instrument through which I am going to study the fluorescence spectroscopic method. Understood?
मैम वाई मतलब जैसे हम लोग बोलते हैं कि यूवी विजिबल स्पेक्ट्रोफोटोमीटर एंड मास स्पेक्ट्रोमेट्री, देन मैम व्हाई दिस इज डिफरेंट?
No, sometimes we say that UV visible spectrophotometry also. That is that concept don't bring that spectrophotometry, but mass spectroscopic method is a method through which we are going to analyze the analytes, the mass of the analytes. But that technique is known as mass spectrometric technique.
Okay, ma'am.
Hello, ma'am.
So,
I have one.
Yeah, tell.
Ma'am, is this like that? In spectroscopy, we involve electromagnetic radiations as a source, but in spectrometry, we don't involve any radiation, electromagnetic
No,
radiation.
no, it's not that. It's not
Like
that.
in mass spectrometry, we involve some chemical method, chemical ionization, or electron spray ionization, like that. Uh, there is
No,
no
I don't
electromagnetic
think.
radiation.
No, I don't think that is the way. But no, I don't think. Mass spectroscopic method also we say. Okay.
But ma'am, most of the time we see mass spectrometry, but all the conventional like UV visible, IR, NMR, we see there is spectroscopy, NMR
In
spectroscopy.
NMR? In NMR?
Yes, yes, ma'am. We are seeing that it is written
See.
NMR spectroscopy.
Huh.
So, ma'am, I'd like to
I think.
intervene here. If you let me please clarify it to you. Basically, as madam said, the
Okay.
difference between spectroscopy and spectrometry is like this. As spectroscopy is the study of interaction of radiation and matter. Okay, that's one bit. And spectrometry basically refers to metry, measurement. Measurement of a
Measurement.
spectrum basically means talking about spectrometry. Okay, like suppose UV radiation interacts with matter, that is UV spectroscopy. When you measure the UV spectrum, that is spectrometry. That's why we say spectrophotometer. Okay, and spectrometer is a generic term. Spectrophotometer becomes specific one, and spectrometer basically is anything which a kind of a instrument used to measure the spectrum. And when you say spectrophotometry, photo comes in when you talk about EM radiation in terms of light. Okay, light photons are used over there. That means the primary is the visible spectrum. UV visible falls in this range. Otherwise, you talk about spectrometry. Okay, thing is, like you're talking about mass spectrometry. In fact, mass spectroscopy technique at all. Because as per our basic definition, scope refers to and when I tell you that in mass spectrometry, there is no radiation coming over there. We are basically trying to hit the molecule high energy and then see what happens to that. Okay, but still, here again, we measure some of a distribution spectrum. Spectrum basically means, okay, like UV spectrum basically get a log as a function of wavelength or frequency or whatever. Similarly, here also spectrometry. So function of m by z values there. It is in that sense a spectrum, and since it also used essentially to decipher the structure of the molecule, so we put it together. So that is studied on spectroscopy, but it is not spectroscopy technique. I hope it clarifies.
Sir, when I measure the spectroscopic results, then it will be spectrometry.
Yeah,
Sir,
the technique of doing it is spectrometry.
Technique. Nice, nice.
sir,
Thank you very much, sir,
okay,
for
sir. Thank you, sir.
clarifying this to me.
Ma'am, I have. Can I ask one more question, madam?
Yeah.
Actually, can we just at the end we'll keep 15 minutes for the discussion? Is it okay?
Okay, madam. Thank you.
Because what I think, if you go through your syllabus, I have gone through it very carefully. The spectroscopy finishing within 7 days is too tedious. Sir also will agree to me. It is a very uh, important topic. However, we are having like 5 blocks and 14 units. First, in between, we'll be discussing. Okay,
Okay,
just
ma'am.
okay. It will be better because we have to move on also. In between, we'll discuss. At least unit one will complete, then we can discuss. Unit two will complete, then we can discuss. It will be better, I think. Okay. Coming to your unit one, where electromagnetic radiation and electromagnetic spectrum is there, that I had already discussed with you through the slides. Okay. The study of different ways in which electromagnetic radiation we can interact with the matter is of great importance in chemistry. Slowly, when you will move through this spectroscopic method course, you will understand it very carefully. Actually, this is a very beautiful course designed, as well as I have gone through the materials which has been provided to you. I'm going through teach you through these materials only. I'm not preparing any my own way of prepare PPTs, because these materials are available to you, and these are very good materials that has been given in IGNO website. So you can go through this very carefully. So this one I have already told you that it is having electric and magnetic field, and both are perpendicular to each other. Then electric field component, when it is interacting with matter, that time we are just dealing with the molecular spectroscopy, IR, EV visible, microspectroscopy, all that will come in that picture. So coming to some characteristics of electromagnetic radiation, here during plus two also you might be knowing the electromagnetic radiation is having certain amplitude, then wavelength is a very crucial role when you are dealing with the studies of other spectroscopic methods, that is designated through lambda, that is wavelength. Then frequency is c by lambda, whereas wave number just c 1 by lambda. These things you must clarify in mind, that what is frequency, what is wave number. These both are not exactly similar. Here you are having c by lambda frequency, and wave number is 1 by lambda, just inverse of lambda in centimeter inverse, we just designate it. Then velocity of light, of course, you know it very well. It is 3 into 10 power 8. Then energy, that is equal to h mu, that is sc by lambda, and where h is having value of 6.6 into 10 power minus 34. These two why I have highlighted, because while doing the numericals you will be facing these things. Always it is not needed that it will be given to you. So these are the basic things you must know when you are going to calculate energy calculation, or you are going to solve some numericals. This is a table given to you, it very beautifully given. That is the characteristics of electromagnetic radiation. If you remember this table, then that's it. You don't have to do anything. When the question is coming like, what is the characteristics of electromagnetic radiation, you can write it in of your own also. That is wavelength, wave number, frequency, and the relationship of these things with the wavelength. Just see relationship with the wavelength, because wavelength, when you are dealing with the electromagnetic radiation spectroscopic part, this is the heart of that. Like which wavelength radiation is falling on matter, then only some type of interaction will happen. As I was telling, it may be rotation, it may be vibration, like that. So related to that, you can study through different spectroscopic method. It may be microwave spectroscopic method or IR spectroscopic method or other methods. Okay. And common units, obviously, these are the part of physical things, physical chemistry. You must remember the units of it. So depending on the wavelength, electromagnetic radiation is of many types and constitutes what is called electromagnetic spectrum. This part I was explaining you in my slide, how it has been divided depending on the wavelength and frequency. And your visible region is the smallest, it is occupying the smallest space out of the all region radiations. Okay. So here I want to tell you what is polychromatic radiation and what is monochromatic radiation. Means polychromatic radiation means it will have consist of different wavelength package type. Okay. Monochromatic radiation means single wavelength radiation. Single wavelength radiation. These things you will be more clear when we move on in our subsequent sections, where we'll be using monochromator in your UV visible spectrophotometer. When you are studying its instrumentation, that time you will be using monochromator, filter, that concepts will come. That time you will be very clear with polychromatic and monochromatic radiation. Now, for the time being, you can understand that monochromatic radiation is a single wavelength radiation, whereas polychromatic radiation is having component of your radiation having multiple wavelength radiation. So this here one question is there: how is electromagnetic radiation is different from sound wave? That is a very simple thing, that electromagnetic waves propagate. How it will propagate? It will propagate perpendicular to electric as well as magnetic fields. Okay. However, sound waves are longitudinal waves. Sound waves are longitudinal waves which will vibrate parallel to the vibration of the molecule that is taking place. So this quantum model of electromagnetic spectrum, I was telling you that from the classical physics, it is not that much clear about the quantum or energy spacing, energy levels of a molecule or particle or radiation. Okay, so this quantum model, which is also known as particle model of radiation, was necessitated by the experimental observations in case of blackbody radiation and photoelectric effect. I was also telling you before about the blackbody radiation and photoelectric effect. Okay, that all heated objects emit electromagnetic radiation, and the wavelengths of these radiations depend on the temperature of the objects. However, here the point I have highlighted, you can see here that energy radiated by a hot surface depends on its nature and surface area besides the temperature. I think it will be very easy for you if you download your materials, you go through today, then again for tomorrow class you get prepared, then again you see, so that we both together can discuss, together can interact in that fashion. As well as I don't think this 2 hour only will be sufficient. Later on also, if you are having any doubt, I am available to you. You can discuss with me. Always we are ready to dissipate the knowledge whatever we are having. Then like blackbody radiation, the existence of photoelectric effect and the related experimental observations could also not be explained by classical physics. However, from the photoelectric effect you get the concept of, that is, packet of energy, which is called quantum of, or quanta of packet of energy. That energy is proportional to your frequency. E is equal to h nu, E is equal to h c by lambda. Also you can write, as we discussed earlier also, frequency is c by lambda. Okay, so these equations you must remember in order to do these numericals. Here it is online class. We are not able to practice the numericals. But numericals, as I told you, this H value, that is Planck constant value, frequency, your C value, that is velocity. These things you must remember. And here you see one numerical is given to you. As well as I found that this study material is also consist of many numericals for your own practice. So that also you must do it as an exercise to you. Okay, here also you can see wavelength is given, you have to calculate the energy. So simple, wavelength is given, you have to calculate the energy. How will do? E is equal to Sc by lambda. Lambda is given to you. So you have to calculate energy. H you know, C you know already. So you can calculate the energy of the photon which is in the green region. How you come to know it is in the green region or red region or whatever region? At 5:35. If I go back, then I'll just show you, since we are discussing this. See, this visible region, it consists of from 400 to 700 nanometer. Okay, and the Bhibgor, you are quite often heard about Bhibgor. Okay, that region. So the green region comes in 500 to 5, this 30 40 region. Okay, that is for the green region. Then we'll move on. See, the due to this wave nature of electromagnetic radiation, various phenomena we observe, that is interference, diffraction, dispersion, then your refraction, reflection, scattering, polarization. All this also comes due to your interaction of your radiation with that of matter. Okay. Interference, due to this interference, you see this coloring pattern. This coloring pattern of peacock feather or coloring pattern of disc that you get due to interference of light, which will have when this monochromatic light is falling through a slit. There will be a slit, opening slit. Then you will have destructive interference as well as constructive interference. This bright spots, whatever you are seeing, that is due to your constructive interference of the wavelets, and the dark spot, whatever you are seeing, that is due to the destructive interference. Okay, so these are the interference patterns. Then diffraction, when it comes to diffraction phenomenon, this phenomenon of bending of wave around the corners of sharp barriers or through narrow openings is called diffraction. Okay, this pencil, this one, that is refraction, sorry. Then diffraction is a wave property which can be observed not only for electromagnetic radiation but also for mechanical and acoustical waves. Diffraction, this phenomena also you can observe for your mechanical as well as acoustical waves, as along with your electromagnetic radiation you can also see. But this diffraction is always slit dependent. That opening, this opening you are seeing, this opening dependent. Okay, so the extent of diffraction through narrow openings or slits depend inversely on the width of the slit. Okay, narrower the slit, greater the diffraction. Slit is narrower, then diffraction will be more. The effect becomes observable when the size of the slit is comparable to the wavelength of the light. Why I highlighted this one? In subsequent material I had seen some questions are there based on this, so I am also highlighting these parts where you'll be seeing some questions, and you can answer when you are attending that questions. Then transmission, it is also a phenomenon when matter and light interaction is there. When the radiation passes through a transparent medium, its velocity is found to reduce. Okay, it's fine. But see, the transmission, when it is getting passed through a vacuum or a clean medium, then it's get transmitted through that medium, and but it depends on the refractive index of the medium also. Here, the refractive index of medium matters a lot during the transmission process. Subsequently, when we are going to study the spectroscopic methods individually, you are having different units for it, then you will be more and more clear towards this subject. Then refraction, this one you might be knowing from a +2, that is when the radiation passes from a rarer medium, say this air, to a denser medium, say glass or say water, then it bends towards the normal to the interface. It bends towards the normal to the interface. Here you can see this is angle of refraction. When you are dipping a pencil in water, then you can see the bending of this pencil. That is due to your refraction method. And this is according to Snell's law. This refractive index relation or frequency of radiation during incident radiation or reflected radiation, this theta, that is angle of incident and refraction, it has been a very nice correlation through this Snell's law. This also you can remember for your examination point of view, as well as to understand these things. Then reflection. This is also another phenomenon where interaction of electromagnetic radiation and matter is happening. When a radiation traveling in medium is incident on a medium of different refractive index, a fraction of radiation bounces back at an angle equal to the angle of incident radiation. That is called reflection of light. That is called reflection of light. Here you can see. Okay. This is incident ray. This down part, both has been written reflected, but this one is reflected ray. Okay. This one is reflected ray. See, here the question is, what do you understand by diffraction of radiation and how it is related to the slit width? What I was mentioning you there while highlighting that parts. Okay. Then scattering is another phenomenon when some part of radiation is transmitted in all direction. That this phenomenon is called known as scattering, and the radiation which is getting scattered is known as your scattered radiation. This is also a phenomena when you are seeing the evening sunset time or morning time, you are seeing this pattern of the sky, that is also due to scattering. Okay. Then polarization concept. These are the small concepts which we need to understand. What is polarization, what is scattering. These things we need to understand when you are dealing with the radiation. That polarization is what? See, from this figure you'll be clear. Anyone wants to say something? Maybe someone unmuted. So I'm asking, when I'm just focusing on this material, I'm not able to go back and see. Okay, fine. So here you just see, you are having unpolarized light, means it will be moving in all directions. Then you can just put a polarizer and it will have a single directional vibration. Okay, single directional vibration. That polarized light waves are light waves in which the vibration occur in a single plane. If your polarizer, you are just tilting it, moving it in different angle, then all that lights will be moving in other direction, or they will have a vibration in another plane, but it will be in uniform plane. Okay. This unpolarized light, they are moving or they are vibrating in different planes. When you are putting a polarizer, you are just getting the light waves in a single plane. So that is what is your polarization is. So interaction of EM with matter, this is what we were discussing. I was showing you the energy level diagrams. There are, this one you need to understand that in my slide I was showing you, you are having some electronic energy levels. These electronic energy levels consist of vibrational energy levels. Then each vibrational energy levels consist of rotational energy levels. This portion of study will be more clear during the emission spectra fluorescence. But in order to move further for the UV also, you need to understand this one, that electronic transitions are also gets accompanied with the vibrational as well as your rotational transition, because this electronic transition energy is more as compared to vibrational transition energy and as compared to rotational energy, rotational transition energy. So you will have some ground state, then fast excited state, second excited state. Then when your molecule is absorbing certain radiation, it may go up to the fast excited state or it may go up to the second excited state. It depends on how much energy it is getting absorbed by the molecule. So there are a number of vibrational energy levels in an electronic state and a large number of rotational energy levels are there in vibrational energy levels too. And this, the difference in energy level is your E2, that is the excited state energy, as well, minus your E1, that is the lower or ground state energy, that is H nu. Okay, when we say something about resonance, when the molecule is absorbing this delta E amount of energy, then only the transition is going to happen. If it is absorbing less than this delta E, then it is not going to get excited. It has to be more energy. When you are sitting comfortably, the energy, the nearby energies around you is different. When someone is giving you punch or giving you some radiation is coming nearer, then the energy, that side of energy will be more. Okay, so that some changes will happen. So basically, three phenomena occur due to this interaction of radiation with matter. Okay, absorption, emission, and scattering. In absorption also many things will be there. In emission process also many things are there. In scattering also various things we will see when we will be dealing with the Raman spectroscopic method part, where relay scattering will come, Raman scattering will come, that parts will come. So basically you are having the three phenomena basically occur, that is absorption, emission, and scattering. And many subsections will be there under this. So when the absorption is happening, that time this concept also we should get clear, that is Boltzmann distribution. Boltzmann distribution. It is related to population of the molecule and the energy difference. Population of the molecule and energy difference. See, if you will understand, if I am having 100 molecules, okay, 100 molecules I am having, and a suitable energy that is more than delta E, the molecule is observing, then I'm going to get a good number of absorbing molecules and going to the excited state. Then you are going to get emission from out of that 100 or out of that 80, or some will dissipate the energy in form of heat, then will come back like that. So but I will get a good amount of intensity of the spectrum. When I'm measuring it, I'm going to get a good amount of intensity. But if I am having this N0 is more, however, this delta E is more also. Means some molecules will be able to observe and go to the excited state. If not only 80 molecules will go to the excited state, then my intensity, resultant intensity will be less. This thermal energy and this population in the ground state and excited state and the delta E, that is the energy difference, matters a lot as far as this absorption and going to the excited state is concerned. This population should be good enough. This delta E should be reasonably that radiation of in certain energy the molecules should observe. Then only some transition will happen, and then only you will be getting some resultant thing in terms of heat dissipation or in terms of your radiation, no, radiative emission. Okay, whether the transition is allowed or not, it is basically governed by certain rules which are known as selection rules. One by one, while discussing the microwave spectroscopy, the IR spectroscopy, the electronic and UV visible, we'll be discussing about the selection rules. Selection rule, all the molecules in nature, we are seeing many molecules, all will be exciting and all will be dissipating, and all type of spectroscopy will be seen. No, there should be a particular nature with that molecule through which you can see certain type of spectroscopic, through which you can study it through certain type of spectroscopic method. There should be a particular radiation wavelength should fall on the matter. Then only you will be able to see. There should be certain characteristics of with the molecule. It will show you the IR, or it will show you the microwave, or it will show you the emission spectroscopic spectrums. Okay, emission spectrums it will show you. Then only by that, taking that spectrums, through that spectrum different parameters, whether it is intensity, whether it is lambda wavelength, whether it is frequency, taking the different parameters of that spectrum, we will be analyzing the molecules. We'll be analyzing the molecules, also the surrounding, the environment near to that molecules, that will be seen. So this atomic absorption, this absorption is of two types: atomic absorption and molecular absorption. Normally, this absorption of UV and visible region leads to transition of outermost electron, while your X-ray absorption involve the transition of electrons that is closest to the nuclei. X-ray absorption. Atomic absorptions mostly deal with we can say it is a part of X-ray absorption. The atoms in the gaseous state can observe UV or visible radiation or X-rays absorption and result in a spectrum consisting of a number of very sharp absorption lines. Okay, this thing also we'll discuss why it is some spectrums are broad, some spectrums are line also. Okay, absorption lines and characteristics of this, these are the characteristics of the atomic species, and this is called a line spectrum. This is called a line spectrum. However, molecular absorption, each electronic energy, as I was telling you, each electronic energy level is associated with several vibrational energy levels, and each of the vibrational level is associated with several rotational energy levels. So the you will be getting not only the electronic transition spectra, it also consists of various fine lines of the vibrational spectrum as well as rotational spectrum. That is why mostly molecular absorption spectrum are broad in nature. We'll be seeing it subsequently. So here you can see this IR and microwave all spectrum are broad in nature. Here IR and microwave region transitions, radiations, only microwave, if microwave region radiation is falling on matter, then there will be transition within the rotational energy levels. Okay, if IR region radiation is falling on matter, it will have transition among the your vibrational energy levels. Also it will consist of rotational as a part of it, because rotational energy level energies are less as compared to vibrational energy level energy as compared to your electronic energy level. This is also known as your Born Oppenheimer approximation, which is not mentioned here in your material, but what I was telling, that electronic energy labels are electronic state labels are having of more energy as compared to vibrational energy level, as compared to your rotational energy levels. Okay, so that is why the electronic spectrums or molecular spectrums generally consist of a series of closely spaced absorption lines. So it appears as a broad band. Here, one example has been given to you. You are getting as a broad band. I will suggest you, if you after the class you just go through the material, you just study of your own elaborately, because class there is some time frame we are having, we have to follow it, and we can discuss the glimpse of idea here, and we are going through online classes, so there is also certain constraints of that, we understand this, but we need to understand certain things which is really essential, then subsequently you have to do of your own also, you have to read of your own also, then you can come back in the next class also, we can discuss. Okay, this one you see what I was talking about. The IR spectrum is reflected in terms of transmittance, percentage transmitters. You see, the line spectrums you are getting. But absorption spectrum for a certain molecule, you are getting a broadband. As it consists of, you are seeing a broadband. As an output, you are seeing a broadband. But it consists of fine lines in between that, of which is your vibrational lines as well as rotational lines. Due to that transition, you are getting that lines. Okay. So, magnetic field induced absorption, that is NMR spectroscopy and ESR, the intensity or radiant power of a line or a band is directly proportional to the number of excited atom. As I was telling you, this you can calculate from the Boltzmann distribution. Very, very essential, that intensity or power of a line, intensity of a line or a band is directly proportional to the number of excited atoms or molecules present in the system. This provides a method for quantitative determination of an analyte. Quantitative determination. How you are getting? If suppose a solution you are preparing, it's having more concentration, a solution you are preparing which is very diluted, okay, so which one will absorb more? If provided that molecule is having certain characteristics to absorb, okay, then the concentrated one will have more intensity of this from the spectrum, you will get more intense spectrum. But there also is certain limitation. Concentration cannot go so high that you will be getting a saturation peak. No, there is limitation to everything. The molecule features, the molecule characteristics matter, the concentration of molecule matter, so that you can deal with the Boltzmann distribution part. Then also what type of radiation the molecule is absorbing, that also matters a lot. Okay, slowly we'll be seeing all molecules will not show you microwave. all spectroscopy. All molecules will not show you IR spectroscopy. That we will be seeing subsequently when we will be discussing IR, when we will be discussing microwave also. Okay, here you see that when you are exciting a molecule M with certain radiation H nu, it is going to the excited state. But how it is coming back? Through the non-radiative relaxation process or through radiative relaxation process. It has to get relaxed in order to come to the ground state. Non-radiative relaxation means through heat dissipation. It is not radiation related. It is through heat dissipation. There we'll be discussing when we'll be discussing fluorescence. That is non-radiative. You are having internal conversion, internal intersystem crossing. All that things are there. But non-radiative relaxation means only through heat dissipation. Some molecule is relaxing through releasing heat and coming to the ground state. Radiative relaxation means it is coming to the ground state by releasing some energy which we are able to see it or we are able to detect it, that radiation through your emission, that you visible region, fluorescence, phosphorescence, or in other technique also. Okay, this is what is your emission, which we call, that is emission. So line spectra, band spectra, I was discussing that line spectra and band spectra, then fluorescence, phosphorescence. These parts will be discussing elaborately in the unit 4. We are having fluorescence and phosphorescence, but this unit is giving a glimpse of all the parts, because first you should have the feelings what you are having, what subsequent classes you are going to study. These phenomena, everything you are going to study, fluorescence, phosphorescence, then Jablonski diagram in that, then Raman scattering, what I was telling you, that is a part of this fluorescence, phosphorescence are part of emission processes. Absorption process is different. Then your scattering phenomenon is different. I was telling you there are as a whole there are three phenomena involved in it. Okay, if a monochromatic radiation is used when the scattered radiation is of same frequency as that of incident frequency, it is called Rayleigh scattering. But if it is different, then we say it to be Raman scattering. Different means then again it may be less, it may be of high intense. Then again two things will come, that is Stokes shift, anti-Stokes shift, that we will be discussing while studying the unit 5, that is Raman scattering. Sorry, unit 4 maybe Raman scattering. So here you see what is the difference between radiative and non-radiative relaxations. Then this table already I had discussed with you through the diagram I had shown you in the PPT, that is type of spectroscopic methods. Here, if you remember that slide, I was telling you when the X-ray, gamma ray radiation falls on matter, that part of spectroscopic study we say molecular spectroscopy, and this X-ray region radiation, diffraction, absorption, emission, fluorescence all also will come. That is X-ray fluorescence, X-ray emission, X-ray absorption, that parts are also there. Then vacuum UV absorption region, then UV visible region where absorption, emission, fluorescence, phosphorescence, that part of spectroscopy will come. Means you can just imagine from now, spectroscopic methods are so vast subject. It is so vast subject. So you have to also put your effort to understand it, to read it. You have to give some time to it. Then infrared region radiation, infrared absorption is also there. Then scattering, Raman scattering, where Rayleigh also will come. See, here also you see the third column, the type of interaction, what I was telling you, rotation of molecule or vibrational rotation of molecule, the interaction, what molecular level interaction is happening. Then NMR, ESR, these things are coming into picture. Okay, so with this, basically we had discussed some things which we can finish within the time limit. I have finished unit 1. Sorry, today I also have to start unit 2. I have planned like this, students, that you can see, you just go through your material. You are having 14 units, 1 4, 14 units. Means if you are having 7 days, we need to cover at least 2 units per day. We need to cover, otherwise this course will not get over. But however, I'm just telling you, you also give some time and study the things, so that tomorrow also we can discuss. But then also you can email to me, that will be better. Instead of using this 2 hour, we can also discuss personally whenever you want. That also can be done, no problem, absolutely no problem. But this 2 hour we have to concentrate here. So the second unit, which is purely your UV visible spectroscopy part, UV visible spectroscopy part. By this time, when we discussed the light matter interaction, electromagnetic radiation interaction with the matter, that time I just told you about everything. Little bit I told you. UV visible spectroscopy, IR or emission, all that things. But here we'll just study elaborately the part of UV visible spectrophotometer. Photometer also will discussed, that is instrumentation of that UV visible spectrophotometer, which laws will follow to study a sample, and how the sample nature should be, everything we'll discuss. So the absorption of radiation in UV visible region of spectrum causes transition amongst the electronic energy levels, as I told you. But these electronic energy level transitions also will accompany the vibrational energy level transition as well as rotational energy level transition. Okay, that is why we discussed these are of band spectrum. These are broad spectrums we get. Okay. However, in the solution phase, the observing species are surrounded by solvent molecules also. Solvent molecule also, and undergoes constant collision with them, with the molecule. These collisions and the interaction among the observing species and the solvent molecules cause energies of the quantum states to spread out. Why I am saying this? If you see this spectrum, here you see, this is in the vapor phase. Even though it is broad, but it is having some line peaks. Okay, when you are taking in the solution phase, there this solution parts, here you see the solution phase is the observing species are surrounded by the solution solvent molecules and undergoes constant collision with them. These collisions and the interaction among the observing species and the solvent molecules cause energies of the quantum state to spread out. Okay, so that is why you are not getting the line peaks. It is broadening of the spectrum you are getting. As a consequence, the sample observed photon spread over a range of wavelength. Thereby, the spectrum acquires the shape of a smooth and continuous absorption peak in solution phase. So here you may get question. Why the absorption spectrum in solution phase are broad in nature, while these are broad and smooth in nature and continuous? Okay, that question also you can respond in this way. So, in order to obtain this UV visible spectrum, the sample is ideally irradiated with the electromagnetic radiation varied over a range of wavelength. Okay. A monochromatic radiation, these things are very important because questions may come What is the basic principle of UV visible absorption? What is the basic principle of IR spectroscopy? What is the basic principle of microwave? What is the basic principle of emission spectroscopy? These are the general questions which you need to understand. Means which wavelength radiation will fall, which type of molecules will show you that spectra, what should be the nature, how will be the instrumentation part, all that things. Okay. So let's move. A monochromatic radiation, that is a radiation of single wavelength. That is a radiation of single wavelength is employed at a time. This process is called scanning. This process is called scanning. Okay. The amount of radiation observed at each wavelength is measured and plotted against the wavelength to obtain a spectrum. This one you can see. This is a spectrum we are getting at the output. But if you understand it very carefully, this language, then in x-axis you are having different wavelength, right? And you are just using a monochromatic radiation, means single wavelength, means corresponding to 200, what absorption you are getting, observance, just 1 point. Then at to 10, what observance, at to 11, at to 12, at to 13. See that वो जो मतलब पॉइंट्स आ रहा है ना, उसको कलेक्ट करके पूरा a broad spectrum you are getting. It is coming as an output, but the amount of radiation observed at each wavelength is measured and plotted against the wavelength to obtain the spectrum. Thus, a typical UV spectrum is a plot of wavelength or frequency versus intensity of absorption. Here, your scale is observance, that is intensity of absorption, and this scale is mostly wavelength. We designate it to be wavelength. Okay, so that is a typical feature of your spectrum of that you are getting through UV visible spectroscopy, or you can say UV visible spectra or absorption spectra also we can say. The UV spectra of substances are characterized by two major parameters, namely position, which you can say through your lambda max, and the intensity of the bands. Okay, position of maximum absorption band called lambda max, and the intensity of band. Here, lambda max, wherever you are having maximum intensity, that is your lambda max. Okay, means wavelength maximum corresponds to your intensity where it is coming as maximum. The lambda max refers to the wavelength of the most observed radiation and is a measure of the difference in the electronic energy levels involved in the transition. The intensity of the other hand is indicative of probability of the transition. If the probability of transition is more, then your intensity also will be more. Okay. And the characteristics of UV visible spectrum depend on the structure and concentration of the observing species in solution. I was telling you before also. It depends on the molecule and the concentration of the observing species in the solution. Therefore, these spectra are extensively used in the characterization and in the quantitative estimation of analyte. If you are having mostly in industries also, you will be finding UV visible spectrum. This is the basic spectroscopic method to study certain things. However, it is having also limitations. You can't study all the things, all molecules or anything. Just a minute. So that is the thing. So what is this analyte is? The chemical species which is to be determined in the sample under investigation, that is known as your analyte. So what type of observing species? It can be organic molecule, it can be inorganic species, which you can just study through your EV visible spectrum. But these organic molecules, the molecular absorption in UV visible region depend on the electronic structure of the molecule. The wavelength of the radiation observed by an organic molecule is determined by the difference in energy between the ground state and the various excited electronic states of the molecule. This one depend on the your ground state energy level as well as excited state electronic energy level. But these organic molecules generally consist of your sigma bond, pi bond, or N, that is non-bonding. Non-bonding electrons also, it consists of non-bonding electrons. So it is having pi electrons or it is having sigma electrons or
Hello.
non-bonding electrons.
Hello. Good
Okay.
evening, madam.
Yes.
Uh, Madam, actually, your
Yes.
screen is not
Hello.
visible.
Oh, is it?
Madam. It's
Ah,
from I think 15 to 20 minutes. The screen is not been
no
shared.
one is telling. Oh, okay,
No, no,
okay.
it
Then
is
I'll
visible.
say,
Ma'am, it is visible, visible.
Uh,
Visible.
okay. Then,
okay, madam. Madam, I am leaving and joining again. Maybe it is my
Ma'am, it's
it is from my side.
maybe.
Yes, madam.
Because I am just sorry, I am just concentrating on my own topic, and as I told you, this frankly speaking, this out of the four thing, this spectroscopic method is very tedious and a very long topic. So you have to bear with me. I am helpless. I can't do anything. Sorry.
Yes,
Okay.
ma'am, you can continue.
I'm just continuing. And whatever doubts you will have, you can just interact with me later on also, no problem. But you just go through your materials. Among all the four topics, this is the biggest and longest topic I have been assigned with. And I'm trying my best to just tell you what you can do through this. And let me tell you, uh, I have done my PhD in fluorescent spectroscopy. Okay, so I basically work on do research on biophysical chemistry and fluorescent spectroscopy under the guidance of Professor Ashok Kumar Mishra, who was the dean of IIT Madras. Also, is a very good spectroscopist. But we basically concentrate on emission spectroscopy during our research part. Okay, sorry, just I'm taking 1 second to have a sip of water. Okay, thank you. So, many of fun, you will find the questions. What kind of transitions, what type of transitions you deal with while studying UV visible spectroscopy? Those have completed your MSc, you know very well that this is the typical questions generally comes. So since you are having sigma electron, pi electron, and non-bonding electron, this there will be transitions like 6 type of transitions you will have: n pi star, pi star, n sigma star, pi sigma star, sigma pi star, sigma sigma star. So this is the energy level. So lowest energy you will have sigma bonding will have lowest energy. Sigma star means, just imagine, to have sigma star transition you need maximum energy. Okay, sigma star transition you need maximum energy. Mostly hydrocarbons are having only sigma star transitions, but studying that is very difficult. Studying that is very difficult. High energy means you can imagine lower wavelength region, and instrumentation, what we are dealing with, the instrument, that also should sense, that also should be sensitive enough to study that. So everywhere certain limitations are there, but we have to understand things, and we have to understand which molecules can show, which are having. Best thing is pi star transition. Those molecules, those organic molecules which are having pi bonds, they will give you. They can give you UV visible spectroscopic UV visible spectrum. You can study that molecules through UV visible spectrum. Okay, so this is the generalized molecular orbital energy diagram and possible transitions for a organic compounds. This you must remember, past different type of electronic transitions. But as I was telling you, that n pi star and pi star can be achieved. These two can be achieved as far as practicality is concerned. The instruments which we are having, UV visible spectrophotometer, the traditional instruments, nowadays again and again modifications are going on. Maybe we'll also see that parts. So these n pi star and pi star are having lowest energy as compared to all. So these two can be achieved by energy that is available in the 200 to 800 nanometer. If you remember when I showed you that electromagnetic spectrum, 200 to 800 nanometer is for the UV visible region part. Okay, so that can be studied there. So these are the transitions. So a molecule which is showing your pi star as well as n pi star transition. So energy means wavelength, it is coming in the longer wavelength, means it will have lower energy, n pi star transition. Then if it is coming in the lower wavelength, then it will have higher energy, pi transitions. So if a absorption spectrum is given to you, and it will be said that it may have n pi star and pi transition, means you are also getting two peaks, then which is n pi star, which is pi star. So obviously lower energy band means higher energy gap, so pi star, and higher in wavelength band means lower energy transition, that is n pi star peak. Okay, so basically these molecules, organic molecules, they are showing some UV visible spectrum or absorbing certain radiations through chromophores. Okay, they will have certain groups, and these are known as chromophores, that is known as color bearing groups. Here you see some questions also will be given that some chromophores are there. Here it is listed. These moieties chromophoric groups are attached with certain molecules. Okay, then what type of transition you are expecting out of that? That can be questioned. From the molecule, the example, you can see whether pi star transition is possible or n bond is also there, so that you can expect the n type transitions or only pi type transitions, because pi star transition is very difficult to get. Pi star is of highest energy. Okay, sorry, I'm mistaking. Sigma. I mean to say sigma star transition. You just see in this whole column, you will not find sigma star transition. These all are n sigma star, n pi star. So by seeing the molecule itself, you can also say which type of transitions you are expecting, whether you are expecting like these two bands or not. Also, you can have an idea from there. Then while doing the experiment in laboratory, whether you are getting these two peaks or not, that you can see. If getting, why? If not getting, why? Then you can analyze out of that spectrum. These theories we are studying here, but practically you can do in experiments, and you can just analyze out of that. The way we are doing the paper publishing, we have to analyze the certain things. So coming to inorganic species, how they are showing the absorption spectrum. A large number of inorganic salts containing atoms with electrons in d orbitals give weak absorption bands in the visible range. The ions and the complexes of the elements of the first two transition series belong to this group and are colored. But why they are, how they are colored? Okay, the question is how they are colored. Here, inorganic species, they don't have a chromophore for it. The color of this species is due to transitions among the d orbitals. So you have heard about dd transitions. These inorganic species are colored. The copper sulfate, all that things are colored. Why? Due to D-D transition. The complex formation of these ions with the solvent molecules or with other ligands leads the degeneracy of the 5d orbitals. As a consequence, these split into groups having different energies, and the electronic transitions from the lower energy d orbital to higher energy d orbital are responsible for these object colors, which is known as completely your package of TD transitions. Okay. The thing I was telling, the blue color of your copper sulfate or violet color of potassium permanganate, you are seeing all that is due to DD transitions. Transition is happening means absorption is going on. It is absorbing certain radiation, that is why it is going to the transition part. Then because without energy, how it will get activated? If I am a normal person, if some energy or some burner will be kept near to me, then only I will feel hotness. Okay. Then the ions of the lanthanide and actinide series are also colored. Okay. However, they don't
Madam,
involve
uh,
S.
madam, in potassium permanganate,
Hmm.
that DD transition happening.
Huh?
Madam, in potassium permanganate, is
Hmm.
DD transition happening?
Potassium permanganate just split the things. Just write the formula and split the things.
Ma'am, it's manganese
Back
plus
and d orbital. Huh?
Ma'am, it's manganese plus 7 in the compound and it's
Okay.
configuration. Then how it is D?
Okay. Okay. Better I will just discuss with you later this part. Okay.
Okay, madam.
Huh. So coming to this part, so lanthanide and actinides are also colored, and these things involve FF transitions, lanthanide and actinide series. So this is the absorption spectra. Uh, this inner transition for inner transition elements, and this is for the transition element. Here, one more thing is there. Except this DD and FF, what we are saying, that complex what it is forming among themselves, there also is charge transfer is happening. Sometimes what happen, that species by itself is not absorbing or by itself is not showing a spectrum, but many a time a given compound that is transparent in UV region starts absorbing after interacting with another species. Understood? Means here one donor group will be there, one acceptor group will be there. This happens if one of the species has an electron donor group and the interacting species has an electron acceptor group. When the two species bind to each other, the resulting species is intensely colored. Okay, this is due to formation of complex between the two species. Such complex is known as charge transfer complex, like your thiocyanate iron. Okay, this is blood red in color, but that species is not alone. It is what to say. If you are separating this one and separating this one, then it is not going to give you color. There is charge transfer is happening from among themselves. Okay, there is some donor group as well as acceptor group, then only the spectrum you are able to get. The radiation observed by this product or complex causes transfer of an electron from an orbital to the donor orbital of the acceptor. Acceptor donor means acceptor donor of this electron. Some is occupied with electron, some is vacant in electron. There is transfer of electron from orbital to orbital, and you are getting a resulting spectrum. So there is your homolumo gap, this energy levels, but the pairing is very good enough to have a overlapping of this homo of your donor and LUMO of your acceptor. Then only this transition or pairing is able to happen. Okay. So coming to this principle of your UV visible spectrophotometry, it is a typical that absorption spectral measurement of a monochromatic radiation is made to fall on the sample taken in suitable container which is called cuvette. That sample holder is known as cuvette. So in such a situation, a part of the radiation is reflected and part is absorbed and part of it is transmitted. When a radiation is falling on the sample, so some will be reflected, some will be absorbed, some will be transmitted. So the intensity of original radiation, that is P0, is equal to the sum of the intensities of the reflected and sum of the of reflected as well as transmitted and your observed radiation. Okay. So now the thing is this all these things I'm not going to say, but here one concept you must understand: the intensity of original radiation is obviously more than that of the transmitted radiation, which we are going to fall, which is going to fall in the detector part and getting amplified. Then we are getting the spectrum. Okay, so it is less intense as compared to an incident radiation because some part will be reflected, some part will be absorbed, then some part will be transmitted. But all these absorption parts has been discussed by Beer-Lambert law, through Beer-Lambert law. Okay, what it is saying? First, initially Lambert law came into picture, then Beer law, then Beer-Lambert law came into picture, and the valid one is most valid one is your Beer-Lambert law. The amount of for this Lambert law is saying that the following observations has been made. The amount of monochromatic light absorbed by a substance is proportional to the intensity of the incident light. Okay, that is the ratio of the intensity of the transmitted and incident light is constant. The second point is the intensity of the transmitted light decreases exponentially. I was telling you, it decreases exponentially when the thickness of the substance through which the light is passing through or increases linearly. Means it depends on the path length also. This path length also, it is depend on the path length, because here you can see the subsequently through this derivation. This you must remember if you are going to get a long question. What is the thing? That ln P by P0, that is P0 is the incident radiation intensity and this is the transmitted intensity is equal to minus KB. Okay, minus KB. This B is your path length. So it is getting directly proportional. Then subsequently I will just say you how to calculate, how to do this. In the Beer law also, you are going to get the relation like this. That is log P0 by P is equal to ABC. P0 by P. Just remember that there it was P by P0, that is why minus sign was there. But it is log P0 by P is equal to ABC. A is the constant, okay, and it is called objectivity. Sometimes in many books you will find log I0 by I is equal to epsilon CL, right? Log I0 by I is equal to epsilon CL. That epsilon, here it is mentioned as A, that is objectivity or extinction coefficient, which we say, whose value depends on the unit of concentration used and is a function of wavelength of the monochromatic light that is getting used. Okay. That is also your objectivity or molar extension coefficient. Then B is your path length of the sample holder, okay, through which the radiation is passing through. C is the concentration. So as a whole, this log P0 by P is also known as observance A. The observance is defined as the logarithm of the ratio of intensities of the incident and transmitted radiations. Okay, A is equal to log P0 by P, which is also A, that is epsilon BC. But transmittance is the reciprocal of, that is minus log of A is equal to minus log of T. Okay, transmittance is P by P0. This relation you must remember as far as your numerical from this UV visible spectrum is concerned. Most of the numericals from UV visible spectroscopy comes from this section, Beer-Lambert's law. What is transmittance? What is the relation of transmittance with observance? And if your intensity is given, you have to calculate the extinction coefficient epsilon. Length will be given, concentration of solution will be given. Here you see the problem also came into picture. That is molar objectivity of substance is given. Molar objectivity means epsilon is given. Calculate the transmittance through a cuvette of path length is given, that is B. Okay, containing the sample concentration is given. So observance is equal to epsilon B into C. So you can calculate A. Okay, you can calculate A, but the question is calculate transmittance. So transmittance is A is equal to log 1 by T. So from there you can calculate A very easily. So here you can see so many numericals only out of that section. So you have to practice the numericals. So here coming to the deviation part, we are left with 15 more pages. I don't know I can finish it in time or not. So deviation from Beer-Lambert's law, here you see, I'm just making you understand of this curve. When you are A is equal to epsilon CB means concentration is directly proportional to observance, you are going to get this B line. Okay, you are going to get this B line. But sometimes, one limitation with this Beer-Lambert's law is it is applicable only to the dilute solutions. It is applicable to the dilute solution. If you are increasing the concentration of solution, then what will happen, you know? Just imagine, you are loading the concentration more. Then the light which is passing through, that is not able to transmit very well. Means that molecules which are in the solution phase, that itself acting as a filter to that radiation. That concept here it is not given, which is known as inner filter effect. Inner filter effect means the same molecule is acting like filter to the radiations. So when this concentration you increase, then also you will get deviation of the absorption. But apart from that, presence of electrolyte also. certain presence of a small amount of colorless electrolyte or which is not observing, just which do not react also chemically with the colored component, that also will show you deviation. That also will show you the deviation from one to one correspondence. It means here you can just imagine, you can also get an idea of the contamination point, right? If you are taking a standard pure solution, getting this B line, but you are adding some contamination to it, you may get A line or C line, means there is some impurity to the solution. So that impurity part also you can predict through this method, UV visible method. Apart from that, some solutions are very pH sensitive. Some solutions are very pH sensitive. Okay. So the chromatation and dichromatation equilibrium, this one, you can see, this is very pH sensitive. In chromate, here it is very clearly mentioned everything. It is very much pH sensitive. In buffer solution you have taken, it will be some color, or if you are changing its pH, then it will be very sensitive to the change in your hydrogen ion concentration. So you will be getting like this kind of spectrum. If originally it is D, then it will be changing. So this point, this isobastic point which has been given to you here, that is showing the equilibrium point. That is showing the equilibrium point because it is very sensitive to this pH or hydrogen ion concentration. Okay, so as I was telling you, many things depend on the nature of the molecule itself. Nature of the molecule itself. Like once I told you, if you remember, selection rule is also there. Like we are talking about general concept, but these general methods sometimes will not be applicable to certain molecules also. Okay, so these things, many these parts are there. Coming to instrumentation part, here I am just explaining you. This is very clearly mentioned. Some radiation source is there. Then that radiation is passing through the monochromator, as I discussed in the previous part. Monochromator, what it will do? It will make the radiation to monochromatic radiation, right? It will have one single wavelength. Then it will fall on the sample cell compartment. Then depending on your nature of the molecule, nature of the solvent surrounding it, then it is going to absorb certain radiation. Then whatever radiation is getting transmitted through this, it will be studied through detector or transducer, which will amplify the signal. Then you will get the signal output as a spectrum. That may be line spectrum, that may be broad spectrum, that we discussed earlier. Okay, if you try to correlate all the things, you will be able to understand very well. But you have to read also. So here, see, these parts are there: radiation source, monochromator, sample compartment, all that things. Okay. So radiation source mostly for UV visible instruments, UV spectrophotometry, which we say absorption spectrophotometry, where we do the measurement. It's that instrumentation part. Okay. So sources of UV region, mostly your deuterium tungsten lamp is getting used. Deuterium tungsten lamp is getting used. Deuterium lamp is responsible for radiation within the wavelength of your 160 to 375. After that, you can have tungsten lamp will take part in the. If in your laboratory or in your industrial point of view, if you have observed somewhere, earlier deuterium tungsten lamps were there in the UV visible spectrophotometry. Okay, where you will get it transition tick sound after this wavelength 160 to 375 scanning will be there. then again your tick sound will be there so that it will be jumping to the your tungsten lamp for the visible range part. Okay, UV visible we are studying, so visible part. But nowadays, mostly the instruments are having tungsten halogen lamps, which can take care from 240 to 2500 nanometer also. But we are just dealing with the UV visible region, so up to 800 nanometer is also fine for us. So tungsten halogen lamps are the good things. So when wavelength selector is coming into picture, this one you must have to keep in your mind while discussing. Radiation source, it is radiating, monochromator is there, sample cell, all these things. Then radiation part is over, the source are giving you radiation. Then wavelength selector will be there, where you will have filter, okay. So this filter will select some radiations to pass on, okay. This complementary colors, Vibgor color is there in the UV visible region. What is this complementary color? Complementary color, an object of a particular color looks of that color because the color is transmitted and its complementary color is absorbed. Okay, if it is absorbing the complementary color, then only it is showing different color. You can see this table is showing you the complementary color chart. Means this is the wavelength of absorption. Color absorbed is different, color it is showing is different. That is known as your complementary color. Monochromator figure, remember the figure of instrumentation. Monochromator, what it is doing? Monochromator are devices that can selectively provide the radiation of desired wavelength out of the range of wavelengths emitted by the source. Okay, so there are two types of monochromator. One is prism monochromator, one is grating monochromator. Prism monochromator, that the prism disperses sunlight. Sunlight is white light into 7 colors. This occurs due to refraction of light. That Indradhanu, we are getting 7 colors of Indradhanu, that we are getting due to refraction of light. The radiations of different color having different wavelengths are refracted to different extent due to difference in the refractive index. After rain, refractive index due to moisture, that air and moisture, all that varies a lot. Refractive index. That is why you say this Indradhanu colors. Okay. So there is also grating monochromator. Nowadays, most preferred monochromator is grating monochromator. It is made by cutting or etching a series of closely spaced parallel groups on the smooth reflective surface on the solid material. Here you can see reflecting surface is there. Incident radiation and it is getting diffracted, and the selection procedure is very, very good over here. Okay. But the thing is, as I was telling you, monochromator means it is just tuning that radiation to be a monochromatic radiation, in single wavelength radiation. Then it is falling on the sample. So here sample handling or sample holders are coming into picture. So these cuvettes are of different type. Cuvettes are of different types, single cuvette, and cuvette path length is very less or it is more depending on your nature of the molecule also. If my molecule is a biomolecule, it is costly. I can take just little amount and study the UV visible spectrophotometer. Then my path length should be less. Okay, if I am quantity is more, then I can go for the 10 path length cuvette. So these are the cuvette holder. Okay, then your detector is coming into picture. Detector, that phototube is there, phototube detector. Photo multiplier tube means the emission radiation which is getting transmitted and falling on the detector, there will have photo multiplier tube, and diodes, which will amplify the things. Then only we'll get good signal. Okay, it will amplify the things. But nowadays, diode array detectors are getting used most often. Diode array detector. It is having certain limitations, though photodiode array is not that sensitive as photomultiplier tube. The possibility of being able to measure a large number of wavelength maker is a detector of choice in the modern fast instruments. Nowadays, these diode arrays are basically used. Then output device, signal processing, where you are getting a spectrum output device. Okay. So here, if you come to the UV visible spectrophotometer, I think there is no time limit. Okay. Anyway, we'll finish it actually. When you come to the UV visible spectrophotometer, single beam spectrophotometer is there as well as double beam spectrophotometer is there. If you go to the labs where you don't have so much fund or facilities, single beam photophotometer was there earlier. I had also used this single beam photometers. Here what happened? See, source is there, wavelength selector is there, okay. Then monochromator will be there, then reference sample is there, then photo detector amplifier output device. Here what you have to see is say always in UV visible spectrophotometer one reference is there, one sample is there, okay. What happened? Single beam spectrophotometer. Here, what happened? First, you have to put the reference, take the absorption of that, then you just take it out, then put the sample, take the absorption again. Okay, that is the complication here. Otherwise, in double beam spectrophotometer, here mirror setting are there. So after wavelength selector, the radiation it is coming through the mirror selector. It is just you can tune it so that part of the radiation is going to your reference, part of going to the sample. Photo detectors too will be there, then amplifier, then output. Okay, you don't have to take it out, rinse it, again put it in the sample. You don't have to do that. So process has been simplified here. Then photodiode array spectrophotometer. Here it is very simple. That sample, one by one sample will be there. Then grating part is there. So here diode array will be there. So in a photodiode array instrument, also called multi-channel instrument, the radiation output from the source is focused directly on the sample. It is more focused, like lasers, it is more focused. Okay. Then coming to analytical applications of UV visible spectrophotometry, that this is very important actually, analytical application, how you are going to utilize it. So qualitative application is not more, qualitative application is practically there, but quantitative applications are there, as I was already telling you how to quantify the things. In terms of qualitative analysis of the analyte, the UV visible spectrometry is of a secondary importance. It is of a secondary importance for the identification and determination of structural details. However, IR, mass, NMR, you mostly use for the identification and determination of structural details. However, UV visible spectrophotometry, we don't use that much. It is of the secondary importance actually for the qualitative thing. Okay, the information obtained from it needs to be supplemented by the IR or NMR or mass spectrophotometry. Okay, this is because of the simple and broad nature of the spectrum. So here you can see the two purple color species, how to identify that, but you can take a spectrum, you will be given two same color type molecules, which is what you can just predict it, which is of for the azodide or a permanganate solution. You can have a knowledge about this, but it is of secondary use. Okay, but as far as quantitative application is concerned, UV visible spectrum photometry has limited application in qualitative analysis of analyte. However, it is probably mostly useful for the tools applicable for the quantitative determination, where you can do analytical determination of the metals, non-metals, analytical determination of organic compounds, then dissociation constants of a organic acid and dye, determination of metal ligand formation constant, determination of kinetic stability also you can find out. But all you will be following Beer-Lambert's law. We have to follow that law over here. So during quantitative determination of what methodology you will be following, forming the observing species means you have to make a solution of the species which we are going to take the measurement. Then selection of the measurement wavelength, you have to choose a particular wavelength where you want to irradiate the sample through the monochromatic thing. Then controlling factors that are influencing the observance means how you are opening the slit window of that radiation. Should be narrow, should be more. It also depends how you are going to get, how you are control that observance. Then validation of Beer-Lambert's law, whether it is getting valid or not. Okay. Selection of the measurement wavelength. In absence of your interfering substances, the measurements are made at an wavelength at lambda max. What I was telling you, observance should be maximum at that point. Okay. Ordinarily, the observance should be measured at a wavelength where there is no interference from the observing species in the solution. One thing you have to remember while doing UV visible spectrophotometry study measurement, you have to use dilute solution. Otherwise, you will not get a smooth peak. It will get saturated, like a flat line you will get, because concentration is too high. As I was telling you, if you try to validate the Beer-Lambert's law, you have to follow this. Okay, if the concentration should not go so high that your intensity level is going up and you are not able to get a good spectrum. How to determine? Suppose some people, your guide or your boss gave you one color solution, told just see what kind of material it may be, because as I told you, it is a secondary method. Again and again, other spectroscopic tools also you have to use to validate the thing. So you'll have a calibrated plot by taking a reference sample whose things are known to you, whose observance is known to you, by varying the concentration whose observance is known to you. So this is a calibration plot. Then now you are taking a unknown solution and taking it observance. Observance is coming like 2.7 something it is coming. Then you can just extrapolate it and you can predict what may be the concentration of that solution. Okay. In order to know the concentration of analyte, you are just adding in the solution. And that should be observing. That is the limitation with these things. Okay. So this is the thing. You can predict the analyte concentration. Some numericals are also there. Oh, I have come to summary point. Good. Thank you. So it is going to be 7:40 also. So here you see, towards the end, you will be getting so many numericals and so many questions. You just read all these questions carefully. Now, just tell me. Oh, I have to stop the recording after the class. Okay. Okay, so I finished 2 units, and among all 14 units, these two are the smallest units. among all 14 units, these two are the smallest units. So we have to just next units, we have to go first. Okay, what you have written? Do you same link? Yes, you have to go through the same link again and again. Oh, thank you, I guess. But I also know there are certain limitations. I'm sorry for that because online, as much as we can proceed further, this is a very vast topic. So you have to bear with me also. But you can just email me. You can also see my profile also. I mostly work on the spectroscopy part and rest other things we'll be discussing. These are the smallest unit we finished. Big units are there, so I'll be running. I'll be running in that sections. Yes, tell Dipti.
Ma'am, I have a
Come.
question. Can we have n sigma star transition always higher energy than pi star?
That energy difference you saw,
Uh,
energy level difference you saw, right?
yes, ma'am.
Remember?
Yes, ma'am. I remember that. But is it a uh, it is a general viewpoint that n sigma star
General
is
viewpoint. It is a general viewpoint.
no deviation that for that?
No, I don't think energy level deviation can be much. Deviation will be there. Deviation will be there when you are dealing with the solvent to solvent defect study. One point you will get deviation when you will be doing the solvent study.
Yes, ma'am. I am taking
Due
the
to the nearby solvent, that n pi star transition that may come lower down or get up. Accordingly, the wavelength may shift. Okay. So, sorry, today we may stop here. It is already time. I'm still in the office. Okay, then I'm stopping this one. Stopping recording. Thank you all. So tomorrow again we'll join with the new units and with the new concepts. Thank you. Okay, thank you, Ojas.
Thank you,
Okay,
ma'am.
thank you.
Thank you, ma'am.
Hello, ma'am.